So we're going to have a Halloween hacking event. Next week, it's either going to be Thursday or Friday. It's going to be like 3 to 4 hours type of thing. We're going to have Halloween-based programming competitions. Show up in costume if you want. There'll be prizes, and there'll be food. So that should be awesome, and I hope to see you all there. And we also are getting further funding from NAU for conferences and miscellaneous other events that you guys stated that you were interested in. So that documentation has been sent to the head of 6 over there. So I'll let you guys all know how that gets situated and handled and how it all works out. And then also, I hope you guys had nice midterms, because I know it can be brutal during midterms week. Who still has any midterms left? Oh, okay. Sorry, guys. But good luck. Oh, wait, it's for tomorrow, isn't it? Prepare well. All right. Well, anyhow, today we have 2 special guests, Lisa and Todd Barraclaw, who are right over here. And Todd Barraclaw works at Lockheed Martin, and he's just going to give us a rundown of who he is, what he's all about, and just a general brief overview. So, everyone, welcome you.
Thank you so much.
That is a very warm welcome. And it was a little cold when I got out of the car, so. All right, well, just to kick it off, take a note of the name, because actually Lockheed is spelled that way originally, the last L-O-U-G-H, so it's kind of fun. They changed the name just so people would be able to pronounce it. So I'm Todd Barraclaw, and Sarah's dad, and I understand the room is mostly filled with computer scientists, software engineers, software developers. So I have quite a bit of software experience in my background, although most of my background was initially in EE and what we call EEE back in the day. So let's kick it off here, and I'm the one kicking it off. Sarah, you ready to come over here and drive for me? So we'll just do a quick intro, little background. The background will flow. Sarah and I think the help of some of the officers, maybe it was Daniel, right? Yep. Put together the agenda. So just trying to show my career path and then kind of get you guys interested in what your correct career path could be, and as you kind of go through. So I've been at this for a while now. You probably could tell by just my looks. So hopefully we'll get through that. Then I'll just touch on a few words on engineering, your future and your focus as I see the world, being 30 years into it at this point. So go ahead, Sarah. So I am extremely pleased to be here and happy to be talking to all you guys, because I think you guys are the next generation. They're going to bring up the next crew. So even if we have one engineer, maybe not even electrical engineer, well, okay. We really do at Lockheed rely on a lot of software development folks. We're a pretty big IT shop that most people don't know. People think of Lockheed in a few pictures that I'm about to bring up. But my current employer is Lockheed. I've actually worked for Lockheed my entire life, but not always as a Lockheed employee. So the way Lockheed was originally spelled was L-O-U-G-H, which is similar to our last name. But they changed it. Lockheed himself changed it so people would pronounce it correct. It's of Irish descent. The worst I've ever been called is Mr. Bark-a-Clonk. I don't know how they got Clonk, but I could see how they could have got Clock, right? And then Sarah, yeah, you've got some Irish, Scottish, and English, and the bar for sure is Irish. The O-U-G-H was kind of Englishy. So my wife Lisa is in the back room. We were married in 1983. 2 daughters, Kate and Sarah. Kate's the older sister. She graduated from ASU, so boo. But then Sarah, Mike, Nick, and my son-in-law Brock, who's married to Kate, are all NAU alumni. And now I have 3 grandchildren, Addison, Evie, and Jesse, and it's like, dang, where's the time gone? So that'll all happen to you guys too, but right now you're in your element and coming into it. So little of my background, I just want to kind of walk through where I've been and what I've done to kind of just map through some of the really cool things I've done, been a part of, and it's been a pleasure to be a part of, and I've really enjoyed doing what I've been doing. So in science, I always liked the thought of a radio. So it's like, how can a radio work, right? So that right away, I'm like, I got to know about transistors and all that kind of stuff. And so I really like the whole thought of a wave propagating through space, or even, you know, air. And so I set off to get my electrical engineering degree. I learned how to fly, got my private pilot's license, and I did all that in my sophomore year in college. So really didn't know exactly what I wanted to do. I always knew I wanted to get into engineering, but didn't know I really wanted to study electronics and electrical engineering. So I got my degree back in 1987 and went to work in '88. But really, the whole transition was to these 7-segment display clocks, right? So the whole digital experience for me was just revolutionizing, right? It was just really cool. And I do remember my 1986 class where we were sitting in and we heard about the Challenger space shuttle. So that's something that'll stick with you for a while. That was a really tragic accident. And then later on in my career, as I'm supporting the space shuttle and events that have to do with vehicles within the shuttle, that was all really kind of came full circle. So I thought that was really fun. So I really kind of started in a company called Cytor. Does anybody know Cytor? So a lot of these companies are all out on the internet now that we have an internet. And I was their first college hire, and I came in as like a greenhorn, right, just ready to go. And you guys will all be the same, but you know, then it's like, okay, hit the brakes a little, be patient. You're gonna learn, you're gonna experience, and the first thing they threw me into was a command and control segment at a satellite test center in Sunnyvale, California, learning about orbital mechanics and trying to figure out how to use math and science to calculate an ephemeris, which is a trajectory of an orbital vehicle. So it's like, okay, well, I didn't study any of that, but all the math and all that really helped me. And then later on, after about 10 or 15 years, I ended up at Embry-Riddle, and I always had a fascination for flight, and I thought, you know, I'm gonna build some digital avionics, because look at that whole display is analog, right? It's like, what the heck? And it even ran with vacuums and all kinds of crazy stuff. So I'm like, we need digital electronics in the cockpit. Well, that all kind of went away, and you'll see that on the next chart. So now I'm more of a senior guy, work on as a chief engineer or chief architect. I'll define those terms. And is anybody familiar with this term right here? So this is high performance extreme computing. So all you guys that are developing code will develop code to run on high performance extreme computing environments, and you'll use your massively parallel computing constructs and use tools like MPI and all that. You write the code, we get the data, we process it and do things with it. Fun things usually. So some hobbies, I like golf a lot. I like our travel, family vacations, gardening. I'm trying to make a hobby out of exercising. I'm not quite getting there quite yet. I used to exercise a lot. I'm definitely joined a gym. Just paying money to be a member right now, but I'm gonna get back in the gym at some point. Okay, Sarah. So Lockheed Martin. Not here officially representing Lockheed Martin. There's a lot of politics, security now. You see everything that happens out on the network. Thanks to you guys with your hackathons. Cybersecurity is a big deal. So it's really important to just kind of be sensitive and not let things out on the internet. All the material that's in this briefing is from the internet. So there's nothing I'm going to say that you won't be able to just go Google search it. But Lockheed's basically built into 4 companies, and Lockheed's a big company. It's hundreds of thousands of people. They make everything from the Aero Group and the F-35. They make everything in the RMS group, stands for Rotary Mission Systems, and mission systems you should key on because a lot of you guys will be building the software that runs the mission system, and that's what's important. I technically work for RMS, but I've never seen a Sikorsky helicopter. Lockheed acquired Sikorsky. Lockheed acquires a lot of companies. You guys might go to work for a company and then you work for Lockheed. Their space division obviously builds satellites, builds launch vehicles. There's the Launch Alliance with Boeing. We put heavy lift boosters up there now. SpaceX and all the commercial guys are trying to put their boosters up and then fly their booster back and land it on a launch pad. Did anybody see that last week? That's just bad A, right? I can't cut you guys are all probably more impression. That is impressive. Very impressive. And then our MFC stands for Missiles and Fire Control. So this is a friendly picture of a THAAD missile which is really meant to intercept a bad guy's missile. So you shoot missiles out of the sky, which takes a lot of software to do that, right? So that's kind of the background on Lockheed, and I'm working in a group that's sort of airplane related now, and I'll get to that as we go through this. So this briefing will take probably about, I call it a briefing, and I make PowerPoint charts. You guys make PowerPoint charts? So sometimes, you know, when we're in big design reviews, it's like death by view graph. Have you guys ever experienced that? Okay, good, because it won't be this briefing. It's a lot more, a lot of pictures. So when I got my private license, as I said, I wanted to really kind of do digital avionics, and right away I got out of school. It's like, no, man, I'm not doing that. I made a bunch of resumes, and I got lucky. I turned in one resume to a friend who was knew the guys at SciTour, which was basically a Silicon Valley club. I grew up in Sunnyvale, California, which is the heart of Silicon Valley. All of the early electronics, all of the technology really of today came out of Silicon Valley, from microprocessors to software, hardware, you know, the whole Silicon Valley fight between Apple and Microsoft, right? You guys all seen that, that movie, what's called Pirates of Silicon Valley? That's a great movie. If you guys are all writing code, watch that movie. Has anybody seen it? Oh, gosh. So you know who Bill Gates is, right? Steve Jobs. You want to have fun with software, watch that movie. It's actually fantastic. So anyway, and all that was in the 80s, right? So you guys obviously weren't born in the 80s, but all my kids were born in the 90s. But so once I kind of got my feet under me, the big things I had to do in orbital mechanics was do tracking and orbit determination, which determined the trajectory of a satellite. And I have a little picture. Because who likes math in here? Okay. So you'll use your math your entire career. You know, I have favorite equations. I can tell you the derivative of x squared is 2x. Okay, what's a derivative? Change of something. Integrate area under a curve. But when you get into the engineering and the science and the math of all that, really you apply it directly. And that doesn't matter if you're talking about a satellite vehicle, an airplane, or a projectile that's going to lose something, you know, powerful, right? It's all physics. So basically, I said I flew satellites, but here's the joke, right? I didn't really fly satellites. I maintained somebody else's software, which I know everybody in here loves to do that, right? Nobody likes to write their own software. Okay. So I personally am a better editor than I am a creator of software, so I didn't mind taking somebody's software and then tweaking it and using it for something else. Because I was an electrical engineer who knew about computers and drew lines, but I had to learn software just because I got into it. I was interested. It was very fun. And basically, one of my first jobs was to study the re-entry of one of our vehicles. And we lived right next to NASA Ames Research Center, so I went over there and I pulled out a book. I'm like, finally, and I just pulled this off the internet. But geez, who remembers how to do any of that, right? Can anybody really look at that equation and go, I got this? Like, nobody, probably. Maybe.
I got the first part.
Okay, good. Yeah. This, I like this, like F equals MA and equals MC squared. I have my favorite equations, you know, like e to the j pi plus 1 equals, let's see, e to the j pi, the imaginary j pi plus 1 equals, it's got another cool number in it.
Nope.
I should put that in previous. 0.
That's what I get.
Euler's formula, yes. So then, I needed to learn about coefficient of drag because we were trying to do a retrograde orbit, inspire the retro boosters, and then bring this thing to where it would land in the ocean, not on somebody's head. So anyway, this was a lot of fun. I did this for a long time. This was kind of like part of my just start out of college, and I went to a company that really I didn't know much about, but I knew what they did was cool, and I thought, well, I can be part of this. This is cool. So then, later on, let's see, I got some pictures. Let's get a picture. So here's kind of like what you would see in your typical math class, right? So just knowing the center of the Earth, right, where you're Earth-centered, Earth-fixed, and you can have a radial distance from here, but all the way out to where your vehicle is, get an initial state vector at time t0, and you know where you are. Then if you're orbiting, you have a certain amount of velocity, and everybody knows if you're orbiting, you just simply are falling past the Earth. You're just missing the Earth, but really you're just in a free fall, but you have so much horizontal velocity, you just keep missing the Earth, so that's how you get in orbit. Well, what you're trying to do is, because you have a bunch of tracking stations on Earth, you got to track your vehicle and point your antenna at it. Well, you got to know all the math to give your azimuth, elevation, and range, so you can acquire that satellite as it comes up over the horizon. And then you talk to it, because you don't really fly a satellite with a stick in the yoke like I showed you in the cockpit. You basically command and control with a bunch of software that says basically turn right, turn left, slow down, speed up, right? Well, satellites don't really turn right and left, but constantly with satellite, you gotta control its orbit and its attitude. So I did this for like 10 years, and I really did enjoy it, and I was never great at the math, but I could code it, and I could look at somebody's code, and I could maintain it, and yeah, I introduced bugs, and didn't do it right, and I was a kid, so they were like, how did that code get in there? So, well, I didn't mean a kid offensively. Okay. But you know, when you start out young, you're green, you just make mistakes, it's just how it is. So typically, if you're just trying to calculate, you're thinking, hey, this guy's gonna be here. Well, he's not exactly where you thought. You observe where he's at, you get another position fix, and then you propagate out where you think he'll be the next time. So the difference between the nominal orbit and your true orbit is what we call your ephemeris generation, and then your orbit prediction. Say, next time I see that guy, like 30 minutes, 90 minutes later, we'll know how to point our antenna and pick it up. So that's all there is to say about that. So in my early career, as I said, I basically was a software engineer, maybe more of a software developer at that time. I distinguish a developer from an engineer, as an engineer kind of plays with a lot of other engineers, and you engineer and you hand stuff off and you define interfaces, and one guy builds component A, another guy builds component B. They've established an interface, they talk to each other, and everybody likes it. I was basically just hacking code that I had to learn for the first time, and then there was a bug in it, and somebody divided by 0 or whatever. But I supported all the launch and early orbit insertion maneuvers, and I basically hung out in mission control complexes at the Satellite Test Center. And I basically was like a fireman. If there was a problem, they'd go, hey, why am I running this command, and why is it not giving me an answer, and can you investigate? You really couldn't fix anything in an operational center. You just say, okay, I know what's wrong. You try to give them a workaround and say, hey, go do this. Oh, yeah, this code, we knew had a problem, go do this. So that was kind of what my job was. And anytime the vehicle would get in trouble, then it was like all hands on deck. And then the fire bells ringing. You're going out and trying to go, oh no, because we don't want a vehicle to fall out of the sky or out of space into orbit. It'll burn up or it'll hit somebody. And some of these vehicles are big, like big as school buses, right? So anyway, we got through with that, and then I basically hung out in the kind of satellites that I worked on. Is we did like remote sensing, so you could see things, and you get to be able to see and map the Earth. You could you'd launch things out of the shuttle, and then the shuttle used the TDRS system, which allowed the shuttle to talk to a relay, and a relay to talk to the ground, and the satellite to talk to the relay, to talk to the shuttle, to talk to the ground, and establish your comms network in space. And then really all that comms network works from hardware and RF and all that, but really it's software that sets it all up, configures it all, and drives it all. And then basically we did the collision avoidance and radio frequency interference, because you don't want big rocks in space hitting the satellite. So if that were going to be the case, or another satellite, you'd say, okay, go right on your next pass. So here's just kind of a picture. I grabbed all this stuff off the internet. I didn't make any of it. Plagiarism was a sincere form of flattery. But there's really a lot of good stuff on the internet, and I just hacked it in. There's one little definition of engineering that I put a reference on, but other than that, all this stuff's right off the internet. But you know, back in the day, Guam was really popular island with RTS, they call it, remote tracking station. I thought that might be West Coast over there, but typically we have tracking stations all around the globe. It's a global network, and we use the TDRS satellite to receive the signals and relay them down to her. So that's how we get the command and control up, the telemetry down, and the data from the payload that's doing whatever it wants to do down to the ground, so that usually you're doing a lot of processing on the ground. And the processing on the ground needs guys that write algorithms, guys that can manipulate light and energy and put all that physics together to eventually get something out of it. Okay, let's go to the next one. Come over here so you guys don't have to keep looking at it. So here's kind of a modern ground station. This is actually for a system called Space Fence that Lockheed put together, but all those little yellow dots, it's all your space junk. Now, back in the day, this was like in a movie, right? You didn't have this. But you do have this now. You have big, huge displays. You have lots of bandwidth, lots of horsepower. Everything can be done in nanoseconds and picoseconds. It's just freaking amazing. And I never cease to be amazed by any of it. It's just like, how do we do all this? But basically, everything we do to help the operations is to make it more timely. So you know something faster, you detect something quicker, and can react and do something about it. And that's important. And even in the business world, you might be stuck doing, not stuck, that's bad. You might be in a business workflow, right? In your business flow and business logic, and you're doing a lot of transactions just to keep track of maybe a stock price or trade stuff. The sooner you can trade and get out when the market's going down, the better. The sooner you can make an alert and give some guy a notice that, hey, there's something going on here, then he can react. And the same thing happens in all of our systems, in our mission systems. The missions change based on the use case and the user. Okay, next. So after I got out of doing all that, I was in basically in Sunnyvale, California until '93, and then that's when we got to Arizona. I said, Lisa, do you want to move to Arizona? She said, nope. I said, well, let's go for a few months. She said, nope, you go first. I don't know if I want to come. And I had a kid. I had 2 kids. It was Katie and Mike. So I went out in like August of '93, and I think I talked you into coming out. You came out in December. September. Oh, so you didn't leave me for that long. That's good. So did I say? Yeah, we got married in '83, and then we went to college together for 4 years, and then we've been married, since. We've mostly all the kids and everything's really good. Sarah's the best because she's the baby, right? You know how that is. Sorry, Sarah. It's okay. She's not gonna be. Okay, so back in the day, again, you're working on these kind of big horses, and it's like, wow, there's a lot of heat and power and cooling, and you need a room the size of, Flagstaff to house all this equipment. But in that day, on that technology, that was the introduction of high-performance computing, and it was IBM mainframes before all that in my first 15 years. And a mainframe was like we were talking about, where you get on a timeshare, and it's got some just antiquated, janky OS, and nothing works, and it's just, and you're sharing it with everybody, and it's clocking at, one hertz, so it's just junk, right? Well, these guys came around, and they did allow us to start parallelizing and giving multiple CPUs, but we didn't even have multiple core technology at this point. So that's why they're so big. Nowadays, everything's shrunk down. You can put a big system on just the chip itself, and a whole chip is a whole computer that, not quite this big, but picture a motherboard just keeps shrinking, right? That's one of the things that's going on is nanotechnology. Everything just keeps shrinking. Pretty soon you can be invisible and you'll still have all this stuff working. And that's what we hear about but you need materials, you need science, you need a way to transmit signals. Because let's face it, nothing works unless it's a 1 or a 0. And so if you got bit stream, you gotta figure out how to encode it, decode it, work on it, and that's how you guys watch your MP, 3 or 4 still. MP3 is more like MP4, all your MP5s, right? And now you can just stream everything over the internet. You instantaneously get it. You just go, okay, yeah, I want to watch that, and boom, you get it. Back in the old days, which is not that long ago, 80s, you were lucky to get, like I said, 10 years. So anyway, we started to take all these mainframes and throw them away. We started to take all these supercomputers and throw them away, and we started to go to a parallel distributed model, client-server, where all a bunch of little machines could all do work at the big house. That moved the data, it moved the processing, but it started to introduce massively parallel processing, which is big today, right? You think of things like Hadoop. You guys, anybody coding in Amazon Cloud or coding with Hadoop or HDFS or any of that kind of stuff?
Parallel programming, mostly in C right now.
In C, okay. So even C kind of went away, right? I'm surprised you're using C and not C++. Someday. We like C++ because object-oriented really is, it's a whole new way. Now you can write like a million lines of code, like just instantiating a class that somebody else wrote and just go, new, star, log, and you just use the method. It's absolutely great. Java's like that. There's other programming languages, but I don't program this much anymore. So, but I did do a lot of C++ back in the day, mostly for user interfaces. So if a guy needs to push a button on GUI, we used to call it HMI. Remember what HMI stood for? What MMI? So MMI was man-machine interface, and that went out real quick. You couldn't have a man add a man, so we went to an HMI, human-machine interface. Then that stuck for a while. Then it became a GUI, graphical user interface. Because I remember being at SciTour, and I'm looking at my boss, and we're writing. It's just all text-based. You just packet stuff on a command line. And I'm like, we really made that. We had this program called GEM. And it was the first kind of intro of an art package for the PC. On a Macintosh, that was the whole cool out. Has anybody seen the Steve Jobs movie?
Which one?
That's a good one, the first one. I only watched the one. I think it came out where he was really fighting his daughter, and he had the whole Lisa. It was the one that, it was probably now, what, 5, 10 years old maybe now? I didn't know there was another one. It's called Jobs.
There's one with Ashton Kutcher and one with Michael Fassbender.
It wasn't Ashton Kutcher. It was the first one.
Okay.
No, I didn't know about the Ashton Kutcher. Maybe I missed that. I was probably on we don't even say surfing anymore. We can't say that. So you know. But anyway, I'm like, boss, look at this. I drew out a picture of the United States. Look at my little mouse pointer. I'm going to click on a state, and I'm going to show you that we can detect that mouse click, bring up information on that state, and that's how we start commanding our software to say we want this, this, and this, and then we'll go do this. Right? It was all point and click. Well, point and click. He's like, dude, that'll never work. I'm like, what do you mean? We're going to be moving towards this kind of thing. He's like, just go back to what he was doing. He's like, he thought I was wasting time. That was kind of another good idea I never did anything with. But obviously, the web came out and HTML and everything's point and click. You don't even have to write software anymore to get point and click out. Right? You just go point, click, 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 compile, and you got a whole GUI built and running for it. So that's all super cool. So the moved away from all of this, moved towards the SunSpark, away from even SunSpark, and went to Intel x86. Now what is everybody loves Intel x86, right? You can't get enough of it. Unless maybe you go to embedded world, then there's smaller, RISC type processors, or what's another small embedded processor? Anybody know? This is not a quiz. I forget. I used to know. But there's all kinds of all your chips in a cell phone. Do we say cell phone anymore? Smartphone. Those are all like a certain type of processor. They aren't necessarily an x86 based. What is it? Oh, ARM. Yeah. Good one. Extra credit for him. Do you guys get units for this, or is this just like for fun?
Yeah, this is for fun. It's a good networking opportunity.
Very good. So basically, when I kind of got in this mid-year path, we took all of this big iron, we called it. Literally, you could think of big iron. This is just like lots of space, lots of power, but it cranked through the data. Now you could do all this on a smaller multi-core chip. But we started getting these workstations. We really did still have. We use this for displaying and commanding and controlling and getting the data to flow collected and processed on the big iron, and then out the door to somebody who wanted it. But we started to then move away from just physical machines. We started going virtual. So everybody's probably virtual in here, like you guys are working. Does anybody use VirtualBox from Oracle? So Oracle, remember they bought Sun. Where's Sun? I could have sworn it happened. Sun Microsystems. They're out of California, right in my backyard. Oracle finally took over because that guy who made a lot of money in databases, and they started ruling the world and the government. And they're like, we're buying Sun. We're going to become a hardware group. So now everybody runs Oracle VirtualBox. I have Oracle VirtualBox on my machine. And I can compile code, and I can look at code, and I can run and go, this is not right here, and then I'll talk to somebody like you guys that will fix it. I can even fix it by hacking it, but usually I stay away from that. But then we started building up big virtual data centers, and the cloud concept started moving around. And we started to not compute on big HPC clusters that were good at just number crunching. We started to build clouds in a 3-layered model. Infrastructure as a service, platform as a service. That's the top one. Software as a service. Then that became very popular, and tooling came out, vCenter from vSphere from VMware. You know, you guys might use VMware Player maybe instead of VirtualBox. But really, you just want to get your nice little Linux environment. Who develops in Linux here? Okay, and who develops in Windows? And then does anybody do like mobile app development for Android or okay? So for us, I mean, I don't care what hardware we're on. Really, we try to start doing a lot of work to abstract the hardware so you don't have to be so connected to it, right? So we want to start becoming very agnostic with our hardware, so that we can swap out hardware. And the reason we swap out hardware is because hardware always goes obsolete. You saw my book back there, some of you. None of that junk's around anymore. Not my little micro board that I made, but literally some of that hardware from the 80s is relevant, obviously. But now we're using a lot of our systems now, where I talked about mission systems, now we're able to really pull together a lot of sensing capabilities that pour data in, but allows us to do really cool things. So a lot of my experience is in what we call remote sensing. So if you have any sensor, now there's a sensor everywhere, right? You can't even drive past a street light anymore without being sensed or surveilled, basically. You got a camera on you all the time. You can't do anything without somebody putting a camera on. So we have systems that can be far away and either use electro-optical technology, which think of a SLR, that's a digital camera. That's your ELIR, electro-optical. It's just a digital camera. Everybody's got one on their phone nowadays. Or IR, where you can actually see heat energy, infrared. And then one of the specialties that we do in Goodyear is what's called synthetic aperture radar. Has anybody ever heard of synthetic aperture radar? Oh, good, we got a SARS units. Okay. Now, do you process data? Have you set up a system around it, or you just know about it?
I just know about it.
Okay.
I'm from Goodyear. So.
Oh, you're from Goodyear.
Yeah,
I work in Goodyear.
Yeah, I've been to Lockheed Martin a few times.
Okay, or did you intern there? Because any of you guys are welcome to intern. I'm not here officially speaking as a lot of you do, but we got all our guys there. You guys come out and we'll put you to work. You'll code something up. We'll throw it into the system. It'll probably be an IRAD or a. But if we're running something really developing for operations, yeah, we'll get you guys going. You just hire on for a few months, go back to school, and then say, hey, I'm a senior, I'm gonna graduate, and then we'll hire you. You interested? Okay. Well, I'll get you in touch with the guys who said I'm not officially able to speak on Lockheed Martin's behalf. But if you're interested, so you know, you can send me your resume. You could reach out to Mark Walgass and guys like that who are the program managers and engineering managers. Right? I'm a chief engineer, chief architect, so I don't manage a lot. I'm kind of seen as a manager, but I'm really not. So, bottom line is, we put sensors in air and in space, and then we build an end-to-end system around the sensor in order to control it and move data, and process data, and build things. So this is kind of a 3D kind of model of being able to detect elevation and actually map the elevation of the Earth through radar, which is basically RF energy pulsing a target, bouncing back, and then us taking it and doing all of our crazy math, where you're basically getting into FFTs and you're trying to figure out where all that energy comes from and sharpening up and you look for a pixel. Well, basically all you're doing is you're just illuminating the target with radar energy. That energy's backing up as you fly. The reason it's called synthetic aperture is your aperture, the more you fly, the bigger your aperture gets. So everybody knows about a camera, right? Really small aperture, no light, but a lot more depth of field. A really big aperture, a lot of light, but a lot less depth of field. When you want to increase your aperture to see more, you just keep flying. And you keep your radar beam on your target, and as you sweep through it, you build this long aperture. You integrate it. I opened with integrating and doing derivatives. Then you can create a map of an image of what you're seeing. And the cool thing about SAR is it sees through clouds and it sees at night. So typically, bad guys like to hide under the cover of night or the cover of clouds. It's hard to hide from SAR. So SAR actually penetrates foliage now too. So if there's a bad guy under a canopy, then think of like everybody that's running drugs in South America, anybody that's trying to run an operation, kidnap somebody, take them into the forest, into the desert. Well, not the desert, it's hard to hide from there. Or easy, yeah, you're gonna be sitting in a cave. Like, sometimes you can even see in a cave if you bounce that radar energy just right. So, bottom line is, there's a lot of sensors. These are all commercial sensors. I've actually personally not wrote the algorithm, the process, the TerraStar X and the radar sat data, but I've got that data and I've built it into my system in a big fat system architecture to allow end-to-end processing of radar sat data. Because if you get data from lots of sources, now all of a sudden you can start getting a better picture of what's going on. So these are some of the ones we play with. There's a bunch of government and commercial SAR satellites that are all on orbit, all just constantly, doing work. There's all the weather satellites up there. Those are IR. If you ever go to NOAA for your National Hurricane Center, anybody hit that site? You go to the GOES site. So Lockheed actually builds GOES, or we call it GOES. There's a GOES East, a GOES West, and they stare in what's called geosynchronous orbit. So you're up there high, 23,000 miles, and you're just falling at the same rate as the Earth is spinning around, so you stay over the same spot. And you use EO and IR to see the hurricanes, and you can now do loops, and now we can make JPEGs and MPEGs, and all that happens via our spaceborne assets. So here's kind of now, as you start looking into HPC, you can see that basically everything starts in the small gigaflop range, giga floating point operations per second, right? And then you start taking a bunch of these, you start baking them all onto a small board, and you start throwing some RAM at it, and then you build a bunch of boards into a blade architecture, and then you start building a bunch of blades into nodes, and pretty soon you end up with a petaflop per second of compute capability. And that's what makes IBM Big Blue, some of these big supercomputers where everybody's trying to figure out how to, a lot of times it's like build a nuclear weapon or something, which is kind of unfortunate. But there's a lot of other cool stuff. That's how we're cracking DNA. It's how we're cracking codes for like bad guys. We always want their codes, right? Cryptology and all that stuff. So that's all kind of what we do. And everybody does. So everybody in the world is doing it, so you guys are in the prime spot to do whatever you want to do with your career and take your software anywhere, because software guys think they're great, hardware guys think they're great, firmware guys think they're great. The reality is nobody can do anything unless everybody relies on a layer below. Just even if you go back to your OSI 7-layer model, which is probably everybody doesn't even remember or care about, but one layer's got to talk to another via a nice, well-defined interface. You got to get up out of your hardware, get up into your hypervisor virtualization layer, up into your OS layer, up into your mission application middleware layer, so you're doing things like MPI, 0MQ, then you get up into your mission services where you write a bunch of common stuff that everybody uses, and then finally you can run your mission app. And then you network it all together, and everybody can talk to everybody. And it all came together because hardware, software, firmware, operations, everybody built a big old system to do what you needed to do. But honestly, at the end of the day, the hardware's always there first. It usually fails first or fails last. And the software guys are always changing something, and we call it built-in job security, because sometimes we think we all just build big bugs just to do a job. But there's always something broke, right? You guys write your software, there's always something you look at it and go, oh man, I shouldn't do that. And it's either core dumping, you guys know core, you just dump core because you just do a big sick fall. And you're like, oh. And you hate that when you're in the middle of an operation, then you got to invoke the workaround because everybody's going, my vehicle's going to fly out of the or fall out of the sky, blah, blah, blah. So with all that said, I've gone through my early days and my mid days, and now I'm kind of in my later path. I started, this is just again off the internet, but Lockheed has associate engineers right out of college. and they turn into like real engineers, I would say. An associate could be one of these guys that are just doing an internship or just hires on for a little bit. You don't even have your degree, but you're super smart and you're motivated and you're energetic and you can think for yourself, and then you can write code and we take it and we integrate, right? And then you kind of get a more senior level. Principal is the level I'm at Lockheed, where I'm considered a principal engineer. At Lockheed, as I was at Double E, they have lots of disciplines, so I became a principal software engineer. But I started as a software engineer, kind of not as an associate. I came in just as an engineer because I already had like 5 or 8 years of experience. And then I worked my way up and started doing software development management. Then I started to do architecture, and then it was more line drawing and concepting and bringing vision to a group of guys that could go actually get a spec and go build something, right? And that's how it has to go. Because usually, like, if you guys come out of school and you show up, you're not going to say, hey, boss, let's go build this big old, massive architecture. Like if somebody handed the plumber the blueprints, right? Well, you hand the plumber the blueprints, he goes, adjusts the pipe, the electrician does the electrical. But in Lockheed, if you're building like a big satellite, that's a lot of work, right? So you got to build not only the satellite, you got to build everything around it to control it, command it, and have it do what it's supposed to do. So now I'm really kind of more of a senior architect. This is a level I really don't aspire to be at as a technical director because one, you're wearing a coat, which I don't mind wearing a coat, and I don't mind getting in front of a group of people when I talk to customers and all that. But I'm kind of more of a hands-on how guy. I'd rather be on a keyboard working and communicating with a team, or other guys could be the technical directors who are trying to go out and win the work and keep everybody busy and get the projects and shuffle around how everybody makes something come together. So we started off on OA. I started moving away from the overhead area and kind of got more into the air and ground side, and I started to just start looking at big ground systems and how all of the architecture comes together. And then we started chasing open architecture and cloud technologies. So on the next slide, I think, Sarah, here's just another diagram on it. But somebody has to build this. Somebody built this is like getting, how a cloud system could work. But everybody uses the cloud. If you put anything in Apple, you back up your phone, or anybody that's doing email, before email comes to a business, you usually send it off to a cloud service that looks for viruses, gets rid of junk mail, does all that, and then it forwards you with mail that's really intended that you want to see. So all that protects your network, protects everything. But basically, hold on, Sarah, I'm going to talk to this a little bit. So up at the top level, really you have all of these servers, application networks, and storage. You have all of the things that get pulled together that you can start using those pieces to build either a private or a public cloud. And then you basically start figuring out how are people going to use my cloud and how I'm going to charge them for it, and how do I give them a portal so they can sign in and say, I'm adding user A through Z, so that I can, keep track of how many emails that come at them, and then I could charge you per email or charge you per storage. And then you get a monetary kind of effort going, and you could start then turning it into a business and making money, right? Because let's face it, we're capitalists, we all like to make money, so you can't have a model that you're going to lose money. So next. Sorry, Coach Katie. So now, I'm kind of now wearing a suit and gray-haired guy, and become more towards the tail end of my career. And I got a lot of life in me. I've kept up with technology, and so really 2016 to present, I've been really doing airborne, and I moved through space and ground, and we're on our 3rd full life cycle development of an open architecture system, and that's all kind of fun work. So let's go to the next slide. So out in Goodyear, the name of their business, and I'm kind of just like a hired gun because I still work for a company that is Lockheed in Colorado, but they're called the Airborne Ground Surveillance Radar. And we can put radars in pods and put processors in pods and fly airplanes and go shoot at targets and keep track of things like the bad guys who are trying to conceal their activities. Okay? And so a radar sensor can build you a map and even show you what's under the canopy in the jungle. So that's all really cool stuff. It can also do moving target indicators. You know, by bouncing radar off something, it changes that Doppler frequency, and we all have speeding ticket by a radar gun. Well, that's a different kind of radar. It's a different kind of radar than when you paint the sky and you want to see an airplane and know how far away he is and how fast he's going and what's his vector, either coming at me or going away from you. SAR lets you bounce radar off of an object, get the data, and then process it and make an image. So these are some of the assets that we actually have out when we fly out there in Phoenix, because it's a test bed for a lot of things. And a lot of times we do things that help us figure out where the technologies go. And we build surrogate development type things. So really the focus is in SWAP. SWAP is size, weight, and power, another acronym. Everybody loves acronyms. Engineers love acronyms. And then HPEC is the high performance extreme computing. So it's really just a modern way of doing everything we've been doing and I've been telling you about, where you bring in your modern message-oriented middleware, your MOM. We use things like ZMQ and MPI. We use a lot of FOSS now. We do all the agile development. Everybody loves agile. Nobody likes to actually do a waterfall and make requirements and then do a design and then architecture and detail design and build it and test it and certify it. That can get you into trouble. But all the tools are super cool, and that's what's good. And then, we're on modern operating systems. We're at CentOS or RHEL. We use Zen, and a hypervisor is called Crucible. It's meant to go on an embedded box. These are things that I'm doing now, and I brought a lot of the things I learned in the HPC world and brought them directly to HPEC, so that you can then start to have a system that's truly hardware agnostic, and what we call it is a software-defined radar processing system, so that you really define your capabilities via software, and that's really good for all the computer scientists, because the more you do in software, the better, right? Whether you're building a software-defined network, software-defined system of any kind, it's all software, then the hardware guys put them out of business. But you're gonna need hardware. You gotta run on something, right? There is no ethereal puffing of a cloud. A cloud is a bunch of servers in a rack in a room somewhere, right? So, and then the way we connect it all is through the high-speed fabric. So in these low swap environments, you gotta kind of go, okay, well, how am I gonna build something? So let's go on to the next one, Sarah. So here's like a typical 3U VPX chassis, where you're basically sticking a computer in each slot, and you start building these up just like a high-performance computer, except you're building them up in a much smaller box, okay? And you gotta make sure it's cooled and all that. Next slide. And then typically what comes out of it is a box about this big, but it could go on a very small platform, or you can make a box a little bigger to go on a big cabin class machine. And guys like Curtis Wright, even that comes back to the Wright brothers when they invented flying. Now they have a big company, they do all kinds of stuff. It's just not like Orville and Wilbur surfing in the wind trying to figure out how to fly. Next. Oh, thank you, Sarah. I was kind of rude about that. Next chart, please. So then how do you really get something like that going? Well, you got to start a risk reduction. Nobody likes to just go off and jump in. You got to start kind of easing into it. Then you create a spec that we could build a system and build software from, which includes the hardware spec too. Then you innovate. So our whole job is kind of to innovate. We want to do things that haven't been done. We want to do things that people say can't be done. And then you go and do them, and that's how we get where we go. The reason we do that is because we all want to be creative, and we create things, and we help people by doing that. So you develop a prototype, and then you try to measure it and see if you're good, and you move on to a more costly box that's more closer to how you want to fly. Or if you just strike out, you go back to the drawing board.
Do you use house of quality for prototyping?
What is that?
House of quality.
No, I don't know anything about that, so it sounds like we need to hear from you. We have quality control, it's called QA, all along the process, but I'm not in QA and I don't know what house quality is, so I'm very interested to hear about it. Sounds new and exciting. There's always something new and exciting. So next, Sarah, please. Is it a technique? Is it a process? What is
it? It is a
house?
process.
Okay. Is it from like the LNG or where does it come from?
Engineering.
Just engineering who?
I learned it in mechanical engineering.
Oh. Oh. So a lot of times what you're saying is the same thing we said like 20 or 30 years ago, they just changed the words, right?
Perhaps, probably.
So maybe that's what it is, but we have always quality every step of the way, and when you got guys in bunny suits building satellites, or everything's tested and checked out through inspection, verification, sell-off qual test we call it. So I'm sure it's all related to that. But here's an example of just like a small rack-mounted 1U blades that kind of build up everything that's in that box, so all the developers can get on it and start parallel programming to start processing and figuring out how to run this thing. Again, this is from Curtis Wright. It's just an example. I played on this kind of box. I log into it and we fan our stuff out, start, stop, and Sarah, next please. So typically, all these are just x86 motherboards using PCIe. So is everybody familiar with PCI? Everybody stuffs a NIC or a GPU or something in their computers. And does everybody do that now still, or are we? Yeah, so if you're an open system, you can go buy your own graphics card, your own NIC, your own whatever you want, video cards, recording, whatever. So, but everything adheres to this PCIe bus. So even in these embedded processors now, the idea is to stick with x86, stick with that PCI architecture, but just shrink it down, make it really small. And then as we go through the standard, we just really transitioned into PCIe 3.0, but even this box that I'm telling you guys about is hanging back at 2.0, and if we use a by 8 data path, we can get up to 4 gigabytes per second for PCIe Gen 2, and then 8 gigabytes per second, mostly doubled for Gen 3. So every time the hardware gets better, you don't want to hang back on 4 gigabytes per second when you can move it at 8. So 4 gigabytes per second is huge. Moving data at 8 gigabytes per second, that's pretty good. Maybe that's just boring to everybody now, but I still find that very exciting. Next. Please. Sorry. Can I get another driver? So here's just an example of a 3U. 3U, does everybody know what a U is? Where it's like in a rack, it's 1U, 2U, 3U. Usually you get like a 70 or 80 U rack that goes in the server room. Well, now you can just put massive 1U things into, this is a 3U, but it slides in, and then this is what you plug the thing into that basically picks up the data plane and the control plane. Then you just now start building a bunch of those. So please go to the next slide. We'll walk through these pretty quick, and then we'll get to my walk-off chart. So this is just a typical drawing where you can see you got a Xeon D 8, 12, or 16 core SoC system on a chip. You have your Gigi switch built right into your board, and then you basically, where all those pins were, this is how you interface and you share data across the however many nodes you have. And so really you got to interconnect it all. Now the fabrics are 10, 40, 100 gigabit per second fabrics, and everybody can talk to everybody on a non-blocking, non-interference basis. And you have 10 nodes that are all moving data at 100 gigabits per second. And that's how we can do super fast processing. But pretty much we're stuck. We tried to do PCIe. PCIe now has a networking standard where you can just stay right on the PCIe bus. You don't have to convert to Gigi or IB. Well, we pretty much still like IB because PCIe is still a little fresh. Next. So here's a typical node architecture where you have a bunch of computing nodes. They all have networking to either get to the PCIe 40 gig network or the 1 gig network. And then you just start building a software system around this technology. Next, here's a typical host adapter card. They call them HCAs, but again, all it is a PCIe card. You hit the PCIe bus and there's the standard. Next. That's just an XMC card that lays into be flat, makes it easy to get on an embedded board. The switch. Next. Nobody cares. I mean, this is hardware. You guys will be bored with this. All this stuff just plugs in now, but you configure it a little bit, but pretty much you can get a COTS processor that is all cabled and comes out of the box. That one thing I showed you, just buy it. It comes all ready to go. And now it's important to throw the software guys at it to code. Next. So then you want to measure. So the most things you like to measure to make sure you're within your performance profile, trying to hit the green. We might hang out in red for a long time until you finally pop into green, but you want to know, are you moving data at rate? Is your latency between your message transfers good? And then your processing times and all that, good for what you're trying to process. And some boring charts just to show how your latency basically kind of goes up as you grow your message sizes. But if you're operating in here, you got like microsecond, picosecond latency, which is really good. And then your throughput kind of stabilizes in a range. And then as you get even bigger and bigger message sizes, now you're really moving the data at the rate you want to be moving at. So 3,347 megabytes per second, which is 3.347 gigabytes per second. 4 gigabytes is the full bandwidth of the fabric. So I'm not really trying to teach any of that. I'm just boring you probably with this, but it all comes together because when you engineer, you got to like what you're doing, right? You've got to work with teams. You got to grow yourself professionally as well as just learn how to get along, because you're always going to be debating or saying whose way is better. And you work through that nice and well. And then we do a lot of cool things that build up our capabilities for people, for security. We're living in really exciting times because I can't keep up, and look at where I started and look at where we're at now, right? So it's like you just never, everything's changing. And so really the question is, what's the next big thing? You know, what is really the next big thing? Quantum computing is very big. The whole cryptocurrency and this crypto, all that blockchain, just doing all that stuff. But what are we really going to do with engineering that's really big? Like, I'd like to see us defeat gravity. That would be really cool. Defeat the gravity well. We're stuck on Earth because we can't launch our vehicles up without billions of dollars and wasted fuel, and everything's physical. And we got to figure a way to defeat the gravitron, right? Or graviton. So this is a boring thing, but I like this actually. I mean, well, these guys are all computer scientists. Who's an engineer in the room? Okay, so we do have 2 engineers. Excellent. Computer scientists do all the software for the engineering too. You guys are all software engineers, I think. That's the way I would like to see you guys all, because if you got a hardware engineer and he's worrying about connecting pins and all that on a motherboard, that's all great. You need it. And all the brains come in the software, but you can put a lot of brains in firmware too. But doing all this together, where you bring math, science, physics, and all that together, to me it's super exciting, and I've enjoyed my career and doing it. And you know, we're moving into pretty exciting times, and you're reading about some of the more controversial things like lethal autonomous robots and the whole moral dilemmas that are going on when we just send a drone up and everybody's like, why is that drone shooting, you know, things? And you start turning it over to the drone, now you're like, oh goodness, right? Next, please. So really, what is the future? Nobody knows, but I know for sure it's bright, because look at where we've been and look at where we are now. And you know in 30 years it's going to be just amazing. And you guys get to usher it all in. Nanotechnology is huge. The whole embedded world, cybersecurity, comms, the whole cryptological area that's going to drive commerce and currency and trade. That's all super cool. AI, machine learning. Hey, I have blockchain up there. I barely know what it is, but I know enough to know what it is. I thought you guys might think it was cool. Then robots, lasers. I mean, lasers now are just amazing. You could do so much with a laser. The same way we bounce radar off something, you could bounce a laser off something called LiDAR or radar. So you can image the elevation and image the Earth by just shooting a very sharp, focused light. Right, Sarah?
Yeah, that's right.
So what laws are we going to render obsolete? Does anybody know what Moore's law and Amdahl's law is? I kind of forgot. Or processors, transistors on a chip double every so many years. And then Amdahl's law is about how much you can parallelize something before you paralyze it so much and no better off than when you were running serial. And then the technology of getting system on a chip. Now we put systems on chips and put lots of chips to build more systems, and everything just grows and grows and grows on itself. It's really, really super cool. And then what do I think your focus should be? This is all part of the agenda, by the way. I'm not just preaching to the choir. I'm just trying to, as I'm now in my kind of sunset years, and I work with a lot of engineers that come from school, that come up with 2, 5, 4 years of experience, whatever. right now, just enjoy being in college and getting a degree and just having fun because it's fun. It really is. And you're going to take all this knowledge and go apply it in the workforce. And as long as you really love what you're doing, do it. So that NASA engineer I was telling you about, his favorite saying was study hard and learn a lot and work smart, not hard. That's what you guys should all do, because you don't want to be just beating yourself up. Whenever you're working on a problem and you start beating your head against the desk and you're like, what the heck? Just walk away, come back, and you'll have solved the problem and walk away and come back. Because you can literally sit at your computer all night, and I do it all the time, and just keep hacking, but you're on the wrong path. It's just, you're on the wrong path. And then, invest in yourself and your family, you know. When you get out there, take a hold of that 401k that all employers are going to offer you now. Invest 100% of what your max is, and they'll match you. And over time, you'll start building a nice little nest egg, and you'll be like me up here standing at code, talking to guys and showing them what you built 30 years ago, which I never thought I would do. But I think it's kind of fun. And then, you don't have to be the smartest guy. I mean, through my career, there's a lot of pride in engineering. If I could warn you against anything, don't be prideful. It's the worst thing in the world. Work with guys. If guys you think they're an idiot and you don't call them an idiot, but just work through it and debate it, and then get into what is a positive decision-making scenario where you go, I got option 1, I got option 2, I got option 3, and option 1 is better than option 2, and you do just a basic trade-off, and then you go, I recommend option 2, and that's your trick. You do that, the other guy's gonna either have to debate you of why his option's better, and then if you both go to management and you recommend option 2 and management says, no, I like option 3, well, now it's no longer your problem. You recommend the good option. When option 3 fails, it's kind of a trick. Well, I told you so, right? And you don't want to do that either, but you get the point. You gotta be a team. And it's a teamwork, and if you debate, it's healthy. If you have big egos and you just want power, and one of the things we realize, knowledge is power, right? Don't be the guy that doesn't share the secret key or the code that unearths everything. Because if a guy's struggling in your group to hack something out, and I say hack very fondly, don't be the guy that's like, I know how to do that, I ain't telling him, right? That's no good. And then be patient. When you start out, come in, be patient, don't stop learning. I mean, there's so much I could still learn, and I probably forgot a lot of what I used to know. But I still know, I think, a decent amount to get by. And then you guys help define the future. That's where it's key. And I really think that the next 10 years, I watch TV and listen and read books and like everything. It's like nothing just comes to you unless you're a pure genius, which is really fun to work with a pure genius. But that's sometimes even hard too, because you just realize, man, how do I keep up with this guy? Right? Go off and define the future. Keep getting smart, and you come up with what's the next cool thing. Because if there's going to be a next cool thing, in my day it was like MP3 file. I had these, tapes and, hey honey, look, I just downloaded a file over the internet. It was like, oh, it took 40 megabytes to save this song before, now it takes 4. Compression and all that was just coming in. We kept marching, and I loved it all. It was just so cool. Because you could put, and if you saw that Jaws movie, that's what he told his daughter at the end. Remember, he said, I'm going to put all that music in your pocket. And it was awesome. It did it. I think that's it. Thank you for your time. I will gladly take any questions, or if I talk too long, what time is it, Sarah? I had a question.
7:42.
Try to make it an hour or less. Who has a question?
I do. I got a question. How much do you know about SAR?
I am not a PhD.
It's okay.
I call it, I'm an honorary member of the Smart Guy Club.
Cool.
I'm not a PhD. I understand the fundamentals of the math and science. I went to the University of Michigan. I took a SAR class and stayed in Michigan for 3 days in Ann Arbor. And SAR was invented in Goodyear, but I'm not a SAR guy. I'm a mission systems guy. I'm an architect that pulls all this together, but I know enough to know when an image looks bad or if there's an artifact in it, but I'm not the guy to say, okay, here's how you fix that image artifact.
Okay, enough of that. So my question is, how, like, the way SAR works, is it taking a continuous picture from when it's like taking those bouncing those radars?
It's pulsing the
So it's
target
pulsing.
and it's integrating the data over time. It's sweeping it all up and trying to FFT it so you know where the power is in the spectrum. And then it's basically developing what we call impulse responses where the energy peaks. And the ratio of that impulse response is directly proportional to the pixel brightness, which you could just have a 256 grayscale with 8 bits, right? In 8 bits, you can make 256 unique values. And you can, if you just light up a pixel from black to full-on white, grayscale with intensity, you can draw that image that I just showed you. But you're really literally painting a scene from a distance by sweeping it in azimuth and elevation and range. And everything's got to be just right. There's angles and dangles. And if you talk to a real SAR guy, it's like, I'm just like, okay. Because you need to know what direction you're going, what your speed is, your altitude, your precision navigation and timing. You're pulsing things down to, microsecond, nanosecond precision.
How far can you zoom in on those images?
You can zoom in a lot, but every image that has a fixed quality associated with it. So the bigger the swath, the more power you got to hit it with. You can control your beam to really tighten up depending on your range. The farther away you are, the more spread you get, the less quality image. So you can make trades between I want a super sharp image versus I just want to see something that can let me see a sharp edge or some glint, we call it, when something bounces back because you see a non-natural object in a natural scene. You know that shouldn't be there, and then you can go do something about it. But you can get accuracies up to 12 inches that I can safely say right now. We're still on. You can get even probably better. Depending on what you know and who you know with, there's a lot of precision. So you can really, a SAR image will never look as good as an EOIR image ever, and everybody's EOIR zealots, I call it. Guys like to see video just as clear as I'm looking at you right now. A SAR, you can never get what I could see you and you can see me. But it does what it needs to do in adverse conditions. So, vehicles that are flying, and, how'd you like to be a pilot of a helicopter search and, combat search and rescue operation when you can't see in clouds and it's nighttime and you got to fly in and get your guys out because they need help. That's a lot of work to do, and SAR helps you do that. SAR as in synthetic aperture radar, not as in search and rescue. SAR is overload. You guys know about overloading acronyms. Everybody says an acronym. It's like, what are you saying? You think you're saying something else, and confusion. And that's part of engineering too. Everybody gets confused. Those are great questions. SAR is really cool. If you got a math background, if you got a signal processing background, if you like to make algorithms that can process light and electrons and photons, and you can channel all that good just talent right into, I'm going to make a really good image, or I'm going to be able to do SAR a different way that gives us even more data. All of the big aerospace companies love guys that can do that, and they're kind of getting hard to find because I'm not saying engineering's any easier, but you got to just be smart and know your stuff. So anybody that's a PhD that's been studying the phenomenology, you guys ever heard of that term, phenomenology? This guy, who's your dad? Do I know? Does he work at Lockheed?
No. My stepdad is an IT guy for the Water and Electrical District for Maricopa. So.
Okay. Yeah, so phenomenology is all about the physics, and then you map that physics with math and science, and then you basically give it to a guy who can code it. And the coding guy is generally not the PhD. The PhD is, anybody use MATLAB in here? So MATLAB, you hit MATLAB and you're like scraping something together, and then you use all the tools, and you're trying to write some equations. But a guy that really gets it, it's like magic, right? It's literally, to me, always magic. Just because I'm always hanging on a lot of times to the PhDs, because they just taught at a different level, let's face it. I mean, they spent a lot of time in school and they're just in it. They're like an expert down to row, you know, whatever. So they get that done, and then they might scab together. That's a bad term. Can you erase that? They might throw together a MATLAB algorithm that's going to work functionally, but it's not going to work optimally. You can never use it in operations. It will take 10 days to do what should be done in 10 minutes or 1 minute. If you give it to a skilled coder that can parallelize it, vectorize it, and streamline it, and pipeline it so that it just goes and you're done, right? And that's where some magic comes, but it gives everybody a job, right? It gives everybody a job if you're a good coder and you know the SAR. And I work with a guy that he's bounced around from many companies. He was at Lockheed, he went to GE, General Dynamics. General Dynamics is over in the valley, downhill. But now he's working for a company called II. He does great programming, but he knows the science a little bit too, so he's a perfect guy. And then you just have guys that do command and control. They don't know anything about SAR, they don't know anything about developing an algorithm or making an algorithm optimized to run, slow and fast. They like the system work, they like the GUI work, they like the web work. They know somebody's got to drive the system. Not everything is automated, lights out, where you just walk away. Who's done that lately where you go, oh, it's all automated, and you come back the next day and like stopped on the second line because it's say faulted, or you forgot to change a permission on a file. It takes a lot of work to automate. Once you get that automation, it helps. But there's a whole power curve to just get automated. So you always need guys that can build buttons that operators or analysts or people push and interact with that system. So the GUI developers are just as important nowadays. Back when I was doing all this, I mean, we were fighting whether or not we wanted to run Windows, .NET on Windows NT versus Sun, Spark, Solaris, which was a Solaris Unix operating system that never failed. Blue screen of death Windows all the time. I got blue screen of death on that computer the other day. I'm like, blue screen of death? You guys know what that is, right? Where it's just hex codes, a bunch of stuff. All your windows are up in VirtualBox. You've got 14 windows across 14 different computing resources. And start over, right? I don't even like bringing up all my windows anymore. I told you guys to be patient because you're young. I'm trying to be patient because I'm a little older. I don't have as much. My wife probably tells me to be patient. I think I'm pretty patient, right, Sarah? Any more questions?
Next slide.
You talk about the space fence.
I could talk a little bit about it. It's basically my parent company, RMS. So Space Fence really is a bunch of land-based radars that do more point detection of objects, not SAR. So Space Fence basically looks up. You've seen some of these other radars that are on the coast that protect our flanks, right? So air defenses, you don't want anybody coming to land something on you. You don't want a plane coming in, you don't want a missile coming in. So we're painting the sky constantly. Those kind of radars are kind of like either sweeping, or now we don't even have a mechanical sweeping radar anymore. Everything's digital, called an AESA. And an AESA is where you have this fat panel that has individual sensors on it that make up a big pixel array of sensors, and now you can sweep your radar beam by just electronically controlling your aperture. So it used to be where you had a mechanical gimbal, and you were flying this way, and you'd be facing this way, and you'd have to say, okay, Mr. Software, go ring, 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 and you mechanically steer your antenna so you could have your exact pointing angle and have your aperture to bounce the radar and receive it. That's all gone now. You just simply fly and you have something mounted on your fuselage, and because it's usually it's a big elongated rectangle with all sensors, and you electronically control the pixels. They're not pixels, they're individual sensors, to steer the beam, bounce the object, return through a receiver exciter, so you can excite the sensor to actually pulse the target, and then you can receive the pulse back. And it's all the math and science that goes into how long it take to get there and how long it take to get back. And everything's the speed of light, so it's anybody know that formula? I could come up with it. It's got lambda, the wavelength. It's got f, the frequency. It's got C
Speed limit.
is speed line, but I think it's, I want to guess. But all I would do is I'd put the units in there. I would go, okay, frequency is 1 over S, lambda is in usually milli something meters, even nanometers. So between that, you could get lambda, I think it's lambda over, F equals lambda over C. But somebody could just do that. Don't you guys do that? Somebody should be able to do that for me right now. No?
Are you talking about Googling?
Look, Google it. Well, we can Google it, but I'd rather do it. Oh, here's a pencil. All right. Do you guys want to do this together? I could be done. Right. I mean, I'm just having fun right now. But C, you know, is the speed of light. The speed of light is in meters per second. That's the units. So you need to get something that is lambda, which is in meters, and frequency equals 1 over S in terms of units. So the formula that ties these all together is going to end up being a multiply. So F equals, it's going to be obviously lambda times C. Why? Because meters,
Yes.
oh wait a minute,
Lambda.
divided by C.
Yeah.
Yeah, C divided by lambda. So you have meters per second divided by meters. Yep, so you C divided by lambda gives you 1 over S. Let's double check our math on that. I haven't done that in 1,000 years.
Yeah, you got it. Yeah, you got it
I
right.
got it right?
Yes.
That's my husband.
Freaking yeah, that's freaking awesome. So that other equation I thought was really fun, and I gave it out. This equation is fun only because it has all the cool numbers. E raised J in engineering is I in math. So we always use J. But we know this breaks down into cosine theta plus J sine theta. Right, so if that's theta, cosine of pi is
-1.
who said that? Genius in the room. There we go. Plus you can look at the formula and go -1 plus 1 equals 0. So yeah, -1. This is nothing because the sine of pi is 0. Plus 1 equals 0. But the only reason that equation is cool to me is we use that equation all the time to figure out your frequency and your magnitude of your waveform that you just pulsed. Because really all you're doing, that's a fancy way of doing trig where everything is a frequency. So when you FFT that, or if you even if just add up all of these, there's the ways that anybody that's digital knows we like digital, so we like 1s and 0s, so we want a square wave, right? This is a 1, this is a 0. Back in my day, 0, 5 volts. Your day, low power processors, everything, were probably around 1 to 3 volts to detect a 1 or a 0. But if you add these three signals together and add them in like some kind of adder function that's done in hardware, you would get a wave that kind of looks, you know, like this. But it's enough to detect that it's looking like a square wave. So if you had an infinite number of signals, you could make any shape wave in the world you wanted. You could make a triangle wave, right? You could make a ramp wave. So you can do all that, and none of us care about that. We'll just give me a signal generator, and I'll hook up a scope, and I'll dial in the waveform. But anything that clocks in a serial interface that you guys will all write, that's all going to be a bunch of 1s and 0s flying at you with a predetermined front end, a bunch of payload, and a predetermined back end, so you can know when to start working at the real data. But if that data is coming in 40 gigabytes per second, that's hauling. But yeah, it's just, I don't know how to do it. I really don't know. But anyway, that was fun, and I'm glad we did that. Now I feel fresh. Any other questions? We can talk about software and C++ and coding and instantiation and polymorphism and overloaded operators and.
Oh yeah, are you guys utilizing data scientists, machine learning, deep learning, and if so, like any way you can disclose?
Yeah, we do all the time. Lockheed is again 130,000 people or something. I don't do anything with it. The guys right across the way who all used to work for Lockheed now started their own business, but we hire them back as contractors. They're all good. They're all good. And you know, what do you really do with it? You know, it's you can do a lot more by looking at all this data mining, but you know, really machine learning, machine conditioning. What we're trying to do is pattern recognition something. So if you're looking at like this square here, and I kind of went like this, and I did that over and over, machine learning would be able to easily tell that my left hand puts this bottle right here because I crossed the boundary and I can detect this bottle, right? But turn this bottle into a BB, can machine learning now know that, oh, it was a bottle, now it's a BB. It can do it instantaneously to allow you to make a decision because a BB just rolled into your table. So it's like, oh, well, the mechanical arms will come and pick up that BB because you don't want to fall on the floor because you got a robot that's doing something. There's all kinds of applications for AI and machine learning, but I'm not an expert, don't even claim to be. I'd have to Google it. But if it's something that you're interested in getting into, there's tons of opportunity because everybody wants to make something smart to the point where maybe we're not getting too smart, right? Like I bought a water heater the other day. It's like, you want a smart water heater? You can get an app on your phone and keep track of how hot your water is in there. No, I just want a water heater. I'll set the water heater to the temperature I want. In the old days it was a dial, you know, an analog thing. My circuit, just heat it up, you knew exactly how hot it was. So I did go with the digital water heater though. And now I can dial into 130 degrees and it's a nice digital readout. It even goes off at night when you're not using it. It comes on in the morning, so it's even got a timer feature. It's all really cool. I'm sure there's some kind of embedded software in it that can tell the time and control the temperature.
Predict when you want to take a shower next.
That would be machine learning and AI. Yeah, it knows based on your shower pattern when it should start to turn on the water.
It's the future. When my popcorn is made before I even know I want it.
There's yeah, and then Internet of Things I had on there. I mean, really, do we really hook up everything to the network? Does anybody know the 5G line I had up there? Did anybody see that in the call, a little call, 5G? That's coming. You guys will all love that. So,
Wait, 5G's here?
5G is like,
You have 5G?
or I don't have it. I said it's coming.
You got $5 grand right now.
It's literally about to be
Yeah.
become a standard. Now, how they roll it out and all I know is they're going to take our whole 4G network and turn it into 5G by using the same infrastructure, but adding, you know, maybe you see a tower every mile now.
Right, I thought like they're like tubular structures they're put on top of
The 4G towers, probably, and then they're going to have to bring more. Because all of those sensors, basically, and emitters that pick up on radio communications, they all have to be networked and make their way to a home base where I can call you and or text you. And it's magically routed, all still through TCP/IP to your phone. Because your phone is either running Linux under the covers, as in the form of Android, or it's running Apple iOS 10X, which is still another form of Linux. Or Unix. Do we say Unix anymore? Do you guys say Unix ever?
Yeah.
Sometimes.
But when you're talking with your friends, do you say Linux or Unix?
Linux.
Linux, yeah. And what was that guy's name?
Linus Torvald.
I read his book. I read a lot of books back in the day.
Yeah, that's fast.
Yeah, because that OS is super key, and that was like releasing because everybody will see they're stuck on Solaris, or they had to pay to get an OS, and then the OS was basically hard coupled to the hardware, which is how Microsoft was one of the pirates. But Microsoft, Bill Gates hired Apple to build his GUI and all that. You know, that whole story is really fun to see. And I think in the end of it all, if you watch some of these movies or read any of the books, it's like they were probably planning a lot of it. You know, they set it up to where it looked like
Let's both be rich.
Yeah, I mean, you know, you gotta leverage it. It's all I'm saying with teamwork. You know, one man or woman could do it all by themselves. Sarah, do you have any questions? I've actually told Sarah a lot of all this.
Is the Earth flat?
Is it flat? In some parts of the world, it is flat. I'm not a flat earther. I just showed you that about orbital mechanics. I'm pretty sure stuff's falling around a spherical, a spheroid, you call
We
it.
also know you can't really say anything. Do you want to write your email up on the board?
For
if
people to
anyone-
get in touch with me if
Yeah,
you want.
yeah.
Yeah, if you want to send me, or you guys really want to come out and, so every year around summertime or whatever, there's something going on. Let's see. I'll do it in the announcement section.
Yeah, you can erase whatever you would like.
No, I can fit this.
Yeah, look for it.
It's just my name with a B. No, that's a lie. That's my Unix. That's my Unix thing. At lmco.com. And just use that one if you want to get to me. I can give you my home email, but that would be kind of dumb. I mean, it wouldn't be, I guess. I mean, you want my home email? Yes, sir.
That says LMCO?
lmco.com.
Okay.
Did it not say that?
Looks like a W.
Oh, LMC, oh yeah, I think that's. LMCO, my bad. Lockheed Martin Corporation. Yeah, we would love to hear from you guys. We're doing a lot of fun work and we never have enough guys. Plus we had a little trouble with they were gonna kind of close the plant and then they didn't. Now we've lost a lot of talent and we wanna restock it. And even if it's, you know, guys that have the coding experience and some math and signal processing background that can come out and help us, we could use the help. And I'm not here officially as a Lockheed guy. I'm just saying, I work with the team and I know where we need resources and we need guys that can work and build and integrate and test and make it work. Not guys that just code and throw stuff over the wall and sit in their office with their headphones on or never come in and make some little program that makes it look like they're online. None of those guys. These guys that can really do work and have fun doing it because they like it. They're not trying to trick it. Is that any more? Well, hopefully this was good and interesting and fun and appreciate your guys' time. Thanks for listening.